Have you ever stood on a station platform, watched a massive train roll in right on the dot and thought, how do they actually pull this off? It's not just big, heavy machinery and steel tracks, right? Behind every single punctual departure and safe arrival is a highly calculated, completely invisible framework of engineering. Today, we're pulling back the curtain on the science that makes modern rail transport tick.
Welcome to my video course on RAMS engineering for railway systems.
Here's a quick look at our roadmap for today's explainer. 1. Introduction to RAMS. 2. Defining the 4 pillars. 3. The mathematics of availability. 4. Inherent versus operational availability. 5. Railway subsystem weak links. And finally, 6. Engineering for resilience. Let's get right into it.
Part 1. Introduction to RAMS.
So, what exactly is RAMS? Well, RAMS is an engineering discipline that integrates reliability, availability, maintainability, and safety into the inherent design of a system to ensure it successfully meets its operational objectives. The absolute key phrase there is inherent design. RAMS isn't just some patch you slap on after a train or a signaling system is built. No way. It's the literal DNA of the system, engineered straight from the very first blueprint to guarantee that things like unreliability and unavailability don't completely derail, pun intended, railway operations.
Part 2. Defining the 4 pillars. All right, let's break down the first pillar, the R in RAMS. Reliability is the probability that a system will perform its required function under stated conditions for a specified period without failure. Basically, it's a measure of how long a piece of equipment, like a track circuit or a signal, can just do its job before breaking down. It's the mathematical confidence we have in the stamina of both our hardware and our software.
Next up is the A. Availability is the proportion of time a system is in a functioning condition and ready for use when needed. Now, while reliability is all about things not breaking, availability is the ultimate end goal for the passenger. It's service assurance. It means when the operator needs to switch a track or dispatch a train, the system is awake, functioning, and ready to go. This is the direct driver of punctuality and, ultimately, revenue.
Then we have the M. Maintainability is the ease and speed with which a system can be restored to a functional state after a failure has occurred. Because, let's be real, things are eventually going to break. And when they do, maintainability measures exactly how fast a technician can diagnose the fault, swap out the busted module, and get those trains moving again. You can kind of think of high maintainability like a highly choreographed Formula 1 pit stop, but for trains.
Finally, the S.
Safety is the freedom from unacceptable risk of harm to people, property, or the environment. And in railway engineering, this is absolute. The other 3 pillars, we have to optimize them without ever compromising this one. It means implementing rigid fail-safes, so if a system does fail, it automatically defaults to a safe state, like immediately turning all signals to red, just to guarantee we prevent any catastrophic accidents.
Part 3. The mathematics of availability.
Okay, so availability is a pretty delicate balancing act, and it's often expressed by this core formula. A equals MTBF divided by the sum of MTBF and MTTR. Let's unpack that alphabet soup. MTBF is mean time between failures, so that's your reliability. MTTR is mean time to repair, which is your maintainability. Honestly, think of it like a giant seesaw. If you want high availability, you've got 2 choices. You can either engineer incredibly robust parts that rarely break, pushing your MTBF way up, or you can make those parts incredibly fast and easy to fix, driving your MTTR way down. In the real world of 24/7 railway operations, shrinking that repair time is often the fastest, most effective lever you can pull to boost overall system uptime.
Part 4. Inherent versus operational availability.
Now, math on a whiteboard is one thing, but mud on the tracks is a totally different story. Every engineer out there faces this harsh reality check, which we can call the funnel effect. Up at the wide top of the funnel, we have inherent availability. That's your absolute ideal design limit, based purely on the hardware's lab specs. But in the real world, a failure doesn't mean an instant repair. That gap between ideal design and real-world logistics shrinks your availability fast. When a part actually breaks out in the field, you've got manual diagnosis time. Then you have logistical delays, like what if the spare part is sitting in a depot 50 miles away? Throw in some administrative delays, and by the time you squeeze through to the bottom of that funnel, you arrive at operational availability. That much smaller number is the true indicator of service quality. It's the harsh reality of what the passenger actually experiences when they're stuck waiting for a delayed train.
Part 5. Railway subsystem weak links. Let's look at some real data and compare two totally different subsystems. Check out the top row. Electronic interlocking, which is basically the digital brain of the signaling system, boasts an astronomical mean time between failures of 100,000 hours, paired with a tiny 2-hour repair time. That yields an incredible availability of 99.998%. But then, look down at the bottom row. The point machine, the heavy gear that physically moves the rails to switch a train's path, has an MTBF of just 2,000 hours and takes a grueling 6 hours to repair. That drags its availability down to 99.7%. Now, that might still sound high, but in a high-density rail network, that 0.298% drop translates to literally hours of catastrophic system-wide delays. Mathematically speaking, the physical point machine is our weakest link.
So why such a massive discrepancy? Simple. Mechanical wear and environmental exposure create the absolute highest downtime vulnerabilities. See, an electronic interlocking system sits safely tucked away in a nice climate-controlled room, but a point machine, it's out there, sitting in the mud, it battles intense mechanical friction every single time it moves, it faces flooding, dust, massive vibrations from passing trains, and extreme temperatures. All that environmental stress directly tanks its reliability. And honestly, just the physical difficulty of getting out to the tracks to reach it drastically inflates the repair time.
Part 6. Engineering for resilience.
Now let's weigh the real cost of fragility against the immense value of resilience. On the left, we have a pretty sobering case study, the Itarsi Junction fire from 2015. A fire completely destroyed a vital relay interlocking room. And because the design lacked geographic redundancy, this single point of failure led to a massive, crippling network outage that lasted over 20 days. Think about that, 20 days of zero availability. Now contrast that disaster with the massive success story on the right, the Delhi Metro. By leveraging modern RAMS principles, specifically using dual redundant servers and modular axle counters, they achieved greater than 99.97% availability. If one system failed, a backup seamlessly took over without stopping a single train. It's night and day.
So the big question is, how do we actually design that level of inherent resilience? Well, here's your engineering toolkit. First up is redundancy. You install hot standby systems. Think dual power supplies or dual processors. If the primary system fails, an automatic switch detects the drop and instantly fails over to the backup, ensuring completely continuous operation. Second is modularity. Instead of hardwiring these incredibly complex systems, you design them with plug-and-play cards. When a component fails, a tech doesn't have to spend hours out there diagnosing a bundle of wires. They just pull out the bad card, plug in a fresh one, and you slash repair times from hours down to mere minutes. And third is hardening. You actively protect against that environmental stress we talked about earlier by using weatherproof cabinets and heavy-duty corrosion-resistant materials for all that vulnerable equipment out in the field.
As we wrap up today's explainer, I want to leave you with one final thought. The smooth, highly predictable journey you experience on a modern railway system, it is definitely not an accident. It's the result of continuous, rigorous mathematical calculation and incredibly strategic design. So next time you board a train, ask yourself, what invisible engineering battles are being fought right now? What redundant servers, modular parts, and hidden fail-safes are working silently in the background just to secure your commute?
Thanks, we can see in next video.